in some time I will share the course content. So first, let me explain the importance of Wireshark and why do we need a Wireshark and how it is used. I'll walk you through that. Then I'll share the course content maybe after some time, and I will walk you through the every topics we have for this training. So my name is Praveen. I have about 12 years of experience in networking. Also, I've been doing a training for Wireshark CCNP. So I'm the instructor for this particular course. So let's get started with this. So sometimes this happens for every network engineer, not for network engineer. In the world of networking, I mean, recent times we are facing a problem with troubleshootings, right? We often face problem with troubleshooting. But the biggest challenge is when whatever we have is we know that we know the protocols, we know how to configure it, but it's very hard to find where is the problem. So to find the root cause of the problem is a bit challenging for everyone. So now Wireshark has become the key component for every engineer to understand and troubleshoot better. You may spend hours and hours to troubleshoot a problem, but it could be a simple problem, but that's something with the logs you can find sometime. But Wireshark helps you to interpret the data sequentially, and you can find the problem. So I'm not talking much about this anymore. Yeah, I think you guys have a fair understanding about our Wireshark, but this training is completely focusing on a deep dive about Wireshark. So let me give you a quick example of a simple demo to demonstrate the use of Wireshark here. So with everything, we are stick to the practical side by side, little bit of whiteboard writing, no much whiteboard writing. So we'll jump into the practical. So let me give you a little glimpse about ARP. So the life of a packet is very, very important to understand the network, irrespective of if you're in the security team, if you're in the cloud. So that's very important, right? So let's see how we can see that in Wireshark. And before that, a quick the background about ARP. If you guys can't see my screen or any comments, you can ping me in the chat. I'll keep an eye on the chat if there is any problem with that. So I think everybody should stick to the same thing what I'm doing here, and you should be able to see me. So let's take an example here. So here I did a quick run through the lab. So this is for understanding. So why I use a BGP for this? So because I want to demonstrate both TCP and ARP together. And also when I talk about TCP, I'll walk you through the TCP handshakes. We call this as a three-way handshake. So I have established a IBGP neighborship with these guys. So this is the second topic we are going to discuss now. So now we are focusing only on ARP. So there is two difference. I had this confusion when I learned about IP communication. So example here, the IP1 tries to talk to 2.2.2. So what happens here, we all know that always your source will be the exit interface, unless you specifically, if you go ahead and do a source interface, if you're not sourcing your traffic from a specific interface, your traffic always leaves from your exit interface. We all know that. So when I want to talk to 2.2.2, the actual communication happens between this is 10 network I used, and this guy is .1, and here is .2. So this is the exit interface, right? So if I try to ping 2.2.2.2, My actual traffic sources from 10.0.0.1. This becomes my source. And my destination becomes 2.2.2.2. So in this case, how ARP works. So in general, a real quick explanation about ARP. So ARP is a address resolution protocol. We all know that the whole objective of ARP is to find the destination MAC address. So here my source is 1.1.1. I know the source IP. And my destination IP is 2.2.2.2. This is my destination IP address. I know my source MAC because I do an ARP request. So I should get an ARP reply back. So this is the IP communication, yeah. But in the ARP request, as I said, we don't know the destination MAC address. If I don't know the destination MAC address, this packet, this particular IP cannot talk to this guy. So that's why whenever you do a first ping, the first packet will be dropped and you get a reply for all the 3 packets. You send 4 ICMP packets, but the first packet is dropped because for an hour. As I said, it also always uses the exit interface. Let's see this, how we can see the same thing in the Wireshark, how it is different to help us to understand better about R. Let me quickly show my config. So here, if you see this Ethernet 0/1, I have configured as 10.0.0.1 here. And this guy on R2, I've configured Ethernet 0/0, I have configured 10.0.0.2. So both are in same network. The point-to-point connection between R1 and R2. So if I check my R table, so I have an ARP entry for 10.0.0.1, 10.0.0.2. So we know this 10.0.0.1 is here. This is .1 and this is .2. So this is in 10 network. So what if I clear an ARP? Now let me try to ping this. I can ping. If I clear the ARP, let me go ahead and do this. If you want to properly flush your ARP table, it's always recommended to shut down the interface, but in production, we can't do that. This is for understanding, for lab, we are doing this. So if I try to do an ARP, I shouldn't do that. I think I did on the wrong interface, Ethernet 0/0. It's brief. It is. Yeah, I can't do it now. So let me quickly open the Wireshark. So I'm capturing the traffic on Ethernet 0/0 here. because this is my exit interface for R1. Go to capture Ethernet 0/1. Going to R1, I'm on R1 here. So you can see, let me stop this capture. Okay. So we got 4 packets for ICMP request. I didn't get any reply because the remote interface is shut down. It's admin down. So I got get any reply here. So what happens when I do a ARP? So for my ARP request, I don't get an ARP reply back, right? So let me go to R2, config mode, and then again, I'm going to turn up this interface again. Oh, shit. Let me close the capture and take it again. So now I get a ping request and the ping reply back because my ARP works now. So without ARP, your communication never happens. So now again, let me try to capture some ARP packets here. Let me take it on R2, Ethernet 0/0 here. That's connected to R1. Okay, so now we captured a few ARP packets. So let me talk about the ARP now. So Cretaceous ARP. This is the ARP it sends by router itself, by an interface. Example, if you got this guy, he's telling that. Let's see the ARP packet inside, but let me give you a little glimpse about what is the Cretaceous ARP. So there are different types of ARP. When I talk about ARP, there is this is a normal ARP. It happens when a host is trying to reach a destination. And maybe you can see when it tries to reach an IP address, a destination IP address, your ARP happens. As I said, you should know the destination MAC address to move your packets. Your IP packet will move only if you know the destination MAC address. So that is ARP, the normal ARP. And the GARP is a Cretaceous ARP is something every host sends an ARP to say that I'm using this particular IP address. So where it helps, it helps to find the duplicate IP address. It will show you that if I'm going to assign the same IP address on both end, example, if I use 10.0.0.1 on R2, and if I use the same 10.0.0.1 on R1, it's going to show that this is a duplicate MAC address. Sorry, this is a duplicate IP address, and I received this request from this particular MAC address. It's going to tell you that from which particular MAC address you got that particular ARP response from. So this is generally whenever you connect a device, a host in a network. Example, if I connect a host to R5 and you got a switch in the middle, and this is a PC connected to it. So example, it is assigned with an IP address 4.4.4.4, an example I'm telling. So this is going to send a Cretaceous ARP response, GR, and so that the R5 will update its ARP table. And it knows, okay, 4.4.4, and this PC is with the MAC address BBCC. So this is mapped to BBCC. But the interesting thing about the Wireshark is if any other host in the same network, example, in the same switch, if you connect other LAN with the same subnet, 4 subnet, if you're trying to use the same IP address 4.4.4, this is host A and this is host B. So this guy is going to say that I am using this IP address. You can't use it. This is a duplicate IP address I'm receiving from. So this helps a lot for your duplicate IP address in your subnet. Say, for example, you may have, thousands of hosts, 500 hosts. Maybe if the host count is too high, it's very hard to go and find every single host. But Wireshark would help you to find it. Now let me show you. The ARP, we'll finish that part. ARP packets, we'll go through the ARP packets, and then we'll talk about the Cretaceous ARP. So this is my capture file. As I said, this is a source. So who sends this reply back for this? 20000, and it is a broadcast. ARP is always a broadcast. It cannot be an unicast in the beginning. Say, for example, this host comes with an IP address source 1.1.1.1. In your ARP packet, this is a source, and it does a broadcast. It does a broadcast for everyone in the same network. And the ARP stays within the same network. Example, it stays only within the 10 networks. So what if this particular packet has to reach other network? We'll come back to that. But here the key components of ARP packets. The source is always going to be the traffic where you're sourcing the traffic from, and your destination will be the broadcast because it doesn't know where it is. And your destination MAC is all F. This is an ARP request. So for this ARP request, this is my source, and I'm trying to reach a destination 2.2.2.2, this case. Since this is not in the same subnet, what it's going to do, this 10.0.0.2 is here, right? This is 10.0.0.1. Let me take a different color to do this better. This is .1 and this is .2. So your ARP request goes with all the 4 key details. Source IP, destination is a broadcast. The MAC address is a destination MAC, is all F. Example, this is a source MAC. This is the interface MAC address, example AA, just for an example. So the destination MAC is unknown, and it is doing the whole broadcast. So it is doing a layer 2 and layer 3 broadcast. Since this is in a different network, now only possibility to reach to network is through .2. So who is the ARP responder for this? 10.0.0.2 would be the ARP responder for this particular ARP request. We'll see that. We'll do that. This is for an ARP with a different subnet. So just imagine this is what happening when you browse a website or whatever it is. This is how the life of a packet in a network. So when R1 wants to reach to R4, first it will do an ARP request to 111. It does an ARP request. And for that, I should get an ARP response back. So here, who is the directly connected here? So 10002 is my ARP responder here. This is my first ARP request. Then from R2, again, it does an ARP request. Because R1 doesn't know how to reach 4.4.4, it is not directly connected, and my ARP request is limited to my local subnet. I can't go beyond this. My ARP limits happens within this domain. So then again, R2 has to do one more ARP request. This is ARP request 1. This is ARP request 1, and this is again an ARP request 2. So finally, it reaches 4.4.4. So for this is how it happens for all over your networks. Example, this is your ISP, and here is your google.com. So the ARP requests keep going like this. Let's see this in the packet. So if I give show IPR, if you see this, the only the directly connected. I know about my local LAN. If you have a VLANs on the switch, and if you have a directly connected devices, you don't see an ARP response for this. I don't know the ARP response for 4.4.4. Even I don't know the ARP response for 2.2.2. If I go here, this R1 doesn't know where is 2.2.2. If I say I don't know where is 2.2.2, in the routing table, you should have a route, but I have no clue about the destination MAC address of 2.2.2, but how my packets is forwarded from R1 to R2. Show IPR. So IP interface brief, exclude and assign. This is up. I do ping. I can reach this, but from here, if I ping, I can ping. So now let's see the packets, IP packets. That's very important, right? We are going from the foundation. So we are not jumping right into the HTTP, HTTPS. So this is the base communication for everything, right? Irrespective of your security or networking. So this is your base communication. So you have to have really a deep understanding about how this exactly works. So ARP is a basic foundation for everything. So let's take the capture and let's see what we can see here. Let me take this. So this is a communication between 10001 and 10002. Let me capture a packet here for 2.2.2. Let me try to ping 2.2.2 again. Let me take a new capture. Let's see. So from here, I'm going to capture a traffic. I'm trying to reach 2.2.2. This is on R2. Let me go to capture Ethernet 0/0. If I do IP.address 2.2.2, it's a filter. So I'm going to apply this for, I want to capture only the traffic from 2.2.2. And ICMP. So I made the filter. I want to capture all the traffic for 2.2.2 network, and I want to see the ICMP traffic. So if you see this, this is a source. Again, as I said, even though if I ping from 2.2.2, sorry, if I ping 2.2.2, but my actual packet is coming from source 10.0.0.1. And if you guys think, are we doing a source-based routing or destination routing? You can remember this. We can discuss in the Q&A session. I'll explain. We are always doing a destination-based routing. So first, if a particular packet has to move from my source to destination, I should have a valid route for it. We all know this. So here I made a static route so that I can reach this. But this routing is happening for what? My destination IP address. So I want to reach 2.2.2.2. So what are the key components I should see here? The source is coming from, so I'm looking at the MAC address here. The source is coming from 10.10. Okay, it takes some time. So it comes from source 10.0.0.2. But actually, I initiated traffic from this router. By default, it chooses my exit interface as a source, right? Let me go back to this diagram. So if I'm trying to ping 2.2.2, but by default, it chooses the exit interface, but that's the only way it can leave the router to reach a destination. So when it leaves a router, it always be your exit interface is your source. It becomes your source. What if I do in a different way? Like if I want to reach to network from a specific source, if you're doing troubleshooting, if I want to reach 2.2.2, I source this traffic from 1.1.1. What happens here? Again, go to Wireshark and see this. So this ICMP communication here, this communication happens only between this 2 and 1, because I am sourcing this traffic from 1.1.1. You guys know this very well, but why what I'm trying to say here. So my source is 1.1.1, but what is my MAC address? 10:10. So let's see whose MAC address is it. So IP interface brief. Hold on a sec. Exclude unassigned. So interface Ethernet 0/0. It's not in the MAC address of exit interface. Shouldn't see the MAC address of my pack. This is also not a MAC address of it. Then what is this MAC address? The source is from 1.1.1. So interface Ethernet 1/0. If you see this, the MAC address matches here. 1010, the last 4 octet. So even though the source traffic is coming from the loopback interface, but the MAC address is totally different. But who is doing a ARP here? So this guy, coming back to this topology. So even though if I'm coming from this 1.1.1, it changes that source MAC address to Ethernet 0/1. So that comes an ARP, right? So here your MAC address changes because of ARP. So as I said, this is how the ARP works in every hop. So if you're doing a troubleshooting with something like this, when you go to the layer, if you check for your layers, you can find this. Is it my traffic is originating from the perfect interface, proper interface? If you have a dual interface here, example, if you have a dual interface, what if your traffic is sourcing from Ethernet 0/0, but that is not something you are expecting, but you can find it using a Wireshark. For that, you have to understand every layer of Wireshark. What are the key components I should see in the Wireshark? And also, if you see, if you click on this in the Wireshark, let me go to the little left. So I take a traffic only for this. Yeah. So for every request, if you click on this, Wireshark will give you an option here. If you see this two arrow marks here, this is an ARP request and I get an ARP reply. If I click on this, this is my first packet. This is my second packet. This is my third packet. So like this, you can actually find for every ICMP request, are you getting an ICMP reply back? If you're missing something in the middle, you can find. And what are the other key parameters you should see? Example, here in our topology, it's very simple. Here, we are pinging from 1 to 2. So we'll come from the layer. So layer 1, we don't know here, this is a layer, it's on the wire. It captured 912 bytes of data. We are looking at the packet 16, number 16 here, 16 and 17. So we know now we got a clue why this MAC address changes. So this is 10001 source. So I see this MAC address. This is a leaving interface here, right? So we know this. This is Ethernet 0/1. And Ethernet 0/0 is this guy, 2000. This is R2. So it is not reaching directly to the loopback interface, but it just passing through my R2 exit interface. What is the R2 exit interface here? This is an R2 exit interface to reach 2.2.2. I can't reach 1.1.1 cannot reach 2.2.2. Both loopbacks cannot be talking to each other directly. It is not possible. Only because of the R, this communication is happening successfully. So that shows us the layer 2 informations. Who is sending to, I mean, who are the source and destinations is involved in this particular communication. And what kind of protocol I'm using here? This is an ICMP. This is a ping reply. If you go here, this is a ping request. For the ping request, I get a ping reply back. And all my parameters are same, no change. So my packet is not broken or it is not tampered in the middle. So that proves my communication. So this is a clean ICMP request and reply. And we'll talk about the TTL. I'll show you how to calculate the TTL and how to do that. When you come to the layer 3 header, so we talked about the layer 2 header. This is the layer 3 header. So my source is 10001 and 2.2.2 is a loopback interface on R2. So I know my source and my destination. But if you see, as I said, your source MAC address is router's physical interface, and this is a physical interface of R2, not the loopback interface. But still your communication is happening because of the ARP. So your layer 3 information will never change. It's going to be static forever. So every time when you see your packet, your only data that keeps changing is your MAC address. If it is not changing, And if it is not hitting the proper MAC address, then there is a problem in your communication. Then you have to check why my traffic is not going there. Is it because of my routing problem? As I said, that's something you should know. I think most of us know about this, but I'm talking about the few who are not aware of it. We are purely doing a destination routing. We're not doing a source routing. So when we want to do a source routing, we have to do a policy-based routing. So that's again too much into routing and switching. So coming back to this is how you have to analyze your packets. We discussed this layer one, layer two, and layer three. We are on layer three. So what are the other key components I should see in layer three? So here the other key thing you have to focus on your layer three header is TTL. So TTL decides how many hops I have to go through to reach a particular destination. So here in this case, this is a directly connected device. I go to here. It's a directly connected device. It is just one hop away, right? What if I want to reach 4.4.4 from R1? So what happens here? A little background about that, and then we'll go jump back to practical. Actually, the working principle of TTL is very interesting. So we are going by packet by packet. We know all about that. So I'm just going right away to the TTL field. So the source is 1.1.1.1. And in the layer 3 header, what you have in the layer 3 header, it just keeps your TTL as 1 first. And it sends the packet here. What is the destination? 4.4.4.4. Can I reach 4.4.4 with TTL of 1? TTL is time to leave, 1 hop. So what happens here? It says TTL exceeded. It sends a TTL exceeded message. Back to R1. So it thinks, okay, I can't reach 4.4.4 with 1 hop. Let me make it as a 2 hop now. Now my TTL becomes a 2 hop. Then once it goes here, it sends a TTL exceeded message and it will decrement the value by 1. So what happens here? Again, it becomes a TTL 1. So it gets to know that, okay, I can't reach 4.4.4 with just 1 hop. Let me make it as a 2 hop, as I said. So it decrements by 1. Now it becomes a TTL of 1 here when it reaches here. And now again, it does a TTL request, right? And again, it sends a TTL exit message. And now the TTL becomes 0 because I got a TTL value 1. TTL 1 minus 1 equals 0. So it sends an exceed message to R2. So that's how, okay, now I can reach this particular router with 2 hops because it's 2 hops away, yeah? 1, 2, 2 hops. Let's see this in the packet capture. This is an R2, so let me try to, I won't see, this is just a 1 hop, so I don't see this decrement here, okay? Let me go back to R5. This is 13001. I'll explain a little bit about this. A simple topology. It's directly connected. 13001 is configured here. It's 13001 is configured on R5. And this is 2. This is 1 and this is 2. So we are just trying to establish a connection between these two so that we can do a trace route from this guy R1 to R5 for 4.4.4. So for that, let me quickly do this little bit of routing I need. So I do router OSPF1 network. Let me do all networks. Area 0. I need to single area. 13.0.0.0 0.0.0.255 area 0. Let me go back to R2 config router OSPF1 network 13.0.0.0 0.0.255 area 0. Just trying to establish a neighborship between these two. So interface Ethernet 0/1. Network point to point. It's a point to point connection between these two. By OSPF network point to point. So I have a connection between R2 and R5 with this, and let me do this. I'm on R2. Uh, so as I said in the beginning, I just used an IBGP connection between all this peering for communication here. I just used this IBGP. And here we are purely running OSPF. So I want to inject my OSPF routes to BGP so that R1 knows where 4.4.4 is connected, or maybe how I can reach 4.4.4 is something I want to tell the BGP because it doesn't know about 4.4. So I'm redistributing this routes from OSPF to BGP. I'm on R2. So run section BGP. Router BGP1. Redistribute OSPF. Process ID 1. Let me go to R1 and see show IP route if I can see 13 network here. So over the BGP, I receive this route. 4.4.4. 1 minute. I think I didn't do I didn't advertise 4 network here. Sorry. Run section route. So I have advertised only this. I want to advertise also the 4 network. Network 4.4.4. 0.0.0. Area 0. I know 13. This is 13.0.0.0 via 2.2.2. This is what? This is 13.0.0.1. If I can try to ping 13.0.0.1. I can't ping it. Oh, I did a redistribution. Okay, I've advertised this on R1. Let me see what's happening here. So section BGP. So IP route OSPF. And see any routes coming from OSPF. So IP OSPF neighbors. Can I ping 13.0.0.1? Ping 13.0.0.1. To run section OSPF. What is that? I think I did wrong. To run section BGP. We distributed this. Wrong command here. I am trying to redistribute the same protocol side. Out. Router SPF1. Network 13.0.0.0. 0.0.0. 255. Yes, 0. Network 2.2.2.2. 0.0.0.0. Yes, 0. Okay, fine. So what is my BGP show run section BGP? So I'm advertising this. Is this command? So I'm trying to redistribute the OSPF routes to BGP. So BGP neighbors can understand. The R1 should understand about this because I'm redistributing this OSPF routes inside the BGP. I'm on R2. Redistribute OSPF. I can ping R2. Okay, let me do a capture now. Let's see. Here, let me do a capture on R1. So Ethernet 0/0 is my leaving interface on R1. So I'm trying to capture the traffic there. Let me do a trace route to 13.0.0.2. Okay, here we got this UDP package. Okay, I'll go only for UDP. Let me try to ping this. What is this? This I'm trying to reach 13.0.0.2. Okay. So from 10.0.0.1, we know this diagram again. This is 10.0.0.1 here. I'm trying to reach 13.0.0.2. And if you see this, the TTL value is 1. So it needs 1 hop to reach a particular destination. So the TTL decrements. So if you compare the old output, you see this 255. It was not decrementing there because that's a directly connected. But with the Wireshark, you can see, is it my TTL is decrementing? What is the source port and destination port is used? Is it blocked? So what kind of protocol it is used? So it is using an UDP protocol for it. So this is a source and this is the destination. So it goes from 10.0.0.1, 13.0.0.2, but it can't reach directly. Then again 10.0.0.2 sends a reply back to 10.0.0.1. This is router 2.2. This is router 1.1. It sends this destination unreachable. So it increments the TTL and it puts the TTL from 0 to 1 here. Then again it sends to 13.0.0.2. It sends a destination host unreachable, and if you see, you can ping this. So this particular IP lives on 10.0.0.2, router 2, right? Here. So IP interface brief 13.0.0.2. Since this is a demo class, we are not doing a big topologies. The focus here is to teach you the how exactly the protocol works. So in the lab, we will do we'll play with multiple protocols, and then we will see different use cases to understand the same thing better. But here, the whole point, as we said, the whole objective is we are trying to reach 13.0.0.2 and reaches here. If you can ping 13.0.0.2, I can ping. So this is how the trace route works. One second, guys. Yeah, guys, I mean, if you have any questions related to what we discussed, you can ask your questions. Somebody asked me a question about Tuan. When you have a minute, I have a question on what duplicate request mean for radius. Okay. I'll give, I think you guys can unmute yourself now and you can ask questions one by one.
Guys, now if you have any questions, you can ask. And
Sir, hello, am I audible?
yes, you are audible.
So in real scenario, I want to capture one switch log. So where should my laptop should connect?
So in switch, basically there is one monitor command. That command you can use to capture the logs, and after that just export that log file and open in Wireshark. That's how you have to do the analysis.
Sir, I didn't get.
So have you tried the monitor command on the switch? So there is a proper command to take the packet capture on the switch. Okay. So using that command, you have to basically take the capture, and after that you have to export those captures into your PC and you have to analyze in the Wireshark.
Okay. So, for example, like I have one switch in my network, and I want Wireshark capture. So I need to run Wireshark in my computer, in my laptop, and then start capturing on my LAN interface. Right,
Yes,
sir?
you have to. Yeah, if you want to capture your packet, then yes, you have to basically run it in your laptop, your Wireshark. Okay.
Okay. And for capturing the logs of network switches or routers, so I need to put run monitoring command in the router or
Yes, same in the router. Yes. So like
okay.
most of the devices, they support basically either they support the TCP dump, either they support the packet capture command, which you can use to basically do the capturing, and after that you have to export those captures and you do the analysis.
Using Wireshark, how we can identify that asymmetric routing? Means what are the parameter it will reflect that it is asymmetric kind of routing?
So there are multiple ways basically. So first of all, what you will see only the one directional packet when you will run the Wireshark captures. So that's how you get to know there is a asymmetric routing is happening, because you will not see any type of reply packet over there. This is the one way. The second way, you have to basically run the capture in your PC and in your and also at the server end, and also in the middle, whatever the network device you are having.